Hello, everyone. Do you all know this course is taught in English? Yeah? Okay, it was mentioned in the inscription. Hello. Okay, so we're going to try to do some hybrid classes. So we'll just stream the class on Zoom. Later I'll upload the videos. But yeah, so there's a webcam here and a microphone here. Hope you had some good holidays. Hope you had good exams last semester, and welcome to the Web of Data, Web of the Office. So I teach this course in English. We're going to give the slides in English, but feel free to ask me in Spanish. Feel free to answer any questions in Spanish. You can use Spanish. I'm going to use English. You can use Spanish. You can use English. You could try with French. I might understand a little bit, maybe Irish. Okay. So today we're going to have an introduction or motivation to the course. So the motivation for the course starts with something we all know, hopefully, called the web. Yeah, so we use the web every day. So the web is now 3 decades old, and it has changed a lot since its inception. Yeah? So in '89 and 1990 is when the web really started. So the question is, what is the future of the web? What will the web look like maybe in 30 more years' time? Okay, so that's a question that we're going to address in this course. So in general, thinking about the web, you might think about some better interfaces, more tactile interfaces, and more fancy visualizations and so forth. So this is one possible view of maybe what you think about the web in the future. You might think about some sci-fi style developments. So in general, I've been working for a long time in this area of research called the semantic web. And I'm going to describe a little bit some of the key concepts today. And the course will be pretty much largely dedicated to the semantic web. So the semantic web is, the course could also be called the semantic web. So the semantic web has been around as a concept for a long time. Not many people know it. Lots of people have maybe heard of it. Lots of people have maybe heard of the concept, but don't know what it is. So if I need to know what something is, what do? I type it into Google search, and then I hit Google search, yeah? And then I'll get some sort of page here. For example, this page describes the semantic web by Tim Berners-Lee. Does anybody know who Tim Berners-Lee is? Nobody in the room? He invented something? Yeah. So he was the inventor of the web. Yeah. So he invented the web. So he also was one of the people behind the semantic web proposal. Yeah, and he says here, or at least in an article called The Semantic Web with some other co-authors, Tim Berners-Lee states, the semantic web will bring structure to the meaningful content of web pages, creating an environment where software agents roaming from page to page can readily carry out sophisticated tasks for users. Yeah, so that's maybe not so straightforward to understand. We'll go through it bit by bit and we'll see. So essentially the idea is that the semantic web will try to structure the content of the web. Yeah, that's the key part. And why? Why do we want to structure the content of the web? In order to allow software, to allow applications to automate tasks on the web. Yeah, that's the concept. So this is not so straightforward to answer what is the semantic web, in the same sense that it's not so straightforward to answer what is the web. Yeah, if you had to answer somebody had never heard of the web before and you had to describe it to them, how would you do it? How would you answer what is the web? Yeah, you could start to describe it technically. You could say, oh, there's this HTTP protocol and there's pages written in HTML and so forth, but that doesn't really capture what the web is, right? Or you could start to describe somehow this interconnected set of computers, this network, but that's really the internet. It's not the web, right? So it's not so straightforward to answer this. So we're going to actually spend a large part of the course answering this question. A more important question to start with is what's wrong with the current web? Yeah. So the current web is great. This is one of my favorite pages. It's called sometimesred.sometimesblue.com. Depending on when you load it, it can be red or blue. So in general, I remember, at least for me, time before the web. I guess for you as well, many of you probably remember not having access to the web. Still, that's slowly fading over time, but so I remember when I was studying in secondary school, I was maybe 14 or so, my brother was building a house and he wanted to create a wooden template for a window so he could fill it with cement, with concrete, yeah? And he wanted to know how to draw an ellipse, an oval, yeah? And he asked me, and I had just learned in class this technique using 2 pins to draw an oval, and he was very impressed with this. This, of course, would never happen today. Why? Because my brother would have Googled it, right? And that would have been the end of it. So the web, we almost take for granted how easy access is to information. If I think about that, or I think about playing video games when I was young and there was no guides, you didn't have any printed guides and you had to find 100 of something and it would take forever, yeah? So the web is great. So Google is also pretty great. So in terms of the web, that's one thing, but what really makes the web great is easy access to information, as I mentioned, to be able to Google or use DuckDuckGo or use Yandex or use Bing or whatever search engine we use. So here we have a Google search, which would be difficult to read. Movie, what's in the box is the search. Anybody want to guess the result? No, nobody remembers. So this is the movie Seven. You'll have to watch it if you don't know the reference. Next search is Da 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 Dum Symphony. Da 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 Dum Symphony. So who said it? Sorry, fifth. Somebody said fifth. Yeah, Fifth Symphony. Yeah, exactly. So these are real results. If you search this, if you type this in, you'll get Beethoven's Fifth Symphony. I guess everybody knows the Da 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 Dum Symphony. And Google can also know what we're looking for. So if we start typing in something, it can give some pretty good suggestions for what we're searching for. So Google in general works very well to help us to get information or to find information on the web, and it provides really impressive search results. So if you want to know more about that, you can maybe try procesamiento masivo de datos. We talk a bit more about these sorts of techniques if you haven't taken it already. So what's the problem with the current web? Let's have a look at a more complex example. So what I'm going to argue is that Google works very well for very common types of searches. Yeah, so for searches that lots of people make many times. Yeah, these very frequent searches. What I'm going to argue is that it's not so good for cases where the search has not been made very many times. Yeah, so for more niche sorts of searches. So we're going to take this example of a user. This user is doing a web user, is doing a report for a university and wants to find all Nobel Prize winners in literature. Yeah. So she's a student of literature, for example. She's doing a report. She wants to find all Nobel Prize winners in literature who fought in at least one war, the year they won the prize, the Nobel Prize, and the year the wars started. Yeah. How would you solve this? So you guys are in, at least not all of you in DCC in computer science, but you're adjacent to computer science. How would you solve this if you had to address this question? Find all Nobel Prize winners in literature who fought in at least one war, the year that the laureates, the winners, won the prize, and the year the war started. Any ideas? Okay. ¿Cuál sería, which would be the more selective or the smaller part? It would be
the second one.
Who fought in at least one war? Okay. Yeah. So we should start with the smallest part, right? And move from there. Yeah. So this is also in databases. If we do joins, we do the same thing, right? So the smallest thing here would be the Nobel Prize winners in literature. That would be the most selective part of the query. Yeah. So what do? We search and we open a page. Maybe we get a list of Nobel Prize winners in Wikipedia. Yeah, there's 140 of them, something like that. What do we do then? Yeah, okay. So for each one, lots of Wikipedia tabs. So we'll search in Google. We'll find the Wikipedia article with the list of all the Nobel laureates in literature. Yeah, so there will be some 100 and whatever, 100 and maybe 20. I'm not sure if there's one every year. We'll find the first one, Sully Putron, and then we'll continue on and look at their profile. Click on their link, maybe in a new tab. Maybe Control F to look for a war or conflict or whatever. I hope we find something. We find I mentioned in this article of the Franco-Prussian War. We open that tab. We get the year when that started. And then we close that tab and then we continue on to the next winner. Yeah. And then we do that 100 and however many times. Yeah. And of course, when we search for war or conflict or these sorts of battle, maybe these sorts of words, we're not going to be sure if we're going to capture all of the wars that might have been relevant, right? Okay. So this is going to be a lot of work. Yeah, this is going to take quite a lot of time. And the question is, does it have to be so tedious? Does it have to be so difficult? So 3 decades on in the web, the way we would try to solve this query would be to start with no results here. I have some pseudocode. For all the Nobel literature winners in the list on Wikipedia, we're going to extract the year of the prize, the year they won the prize. And then we're going to search within this page. We're going to search for terms like war or conflict or battle using Control F. And then for all the war in wars, all of these wars that we found, we're going to click that link and we're going to go and find the year that the war started. And we're going to add this information to our results with the Nobel literature winner, the year of the prize, the war, and the year of the war. Yeah. And return the results. So that's a whole lot of manual work. And the question is, do we really need to do that? Okay. So in general, what we'd like to be able to implement is a function whereby essentially we have this magical semantic web results. A user can pose a query that could be relatively complex on the web and receive the results directly. Yeah, it's just like this. Yeah. So they somehow specify what they're looking for and they get the results and they don't have to go to all these different pages and collect information from all these different sources. So, okay, we need to be a little bit more explicit on what this function magical semantic web results might look like, how we could implement it. And that will be a large part of the course to discuss a possible proposal for this. So this is a pretty hard query, a pretty hard question to answer on the web currently. Why is it difficult? Why is it so difficult? So thinking about why it's difficult is a key reason or key motivation for the semantic web and for this course. Yeah. The first thing is that Google is excellent at finding web pages where essentially there's just one page. Yeah. So if the answer is already there, if somebody has already published a blog post doing an excellent analysis of this, Google is perfect. Yeah. However, if the answers you're looking for are not on one page, then it could be a lot more difficult. Yeah, because you have to do the manual integration yourself. So why is this query hard? Because nobody has done this before. And why have they not done it before? It's quite specific. Yeah. It's not something that, many users, it's not going to drive a lot of traffic to a web page. It's not going to be a very high in demand type of query. So for that reason, it's quite difficult. So this is a very niche specific example. I think it's important to highlight that this is not the only kind of case where people are doing university reports on a very specific topic. It can also be within the context of a particular user. For example, if you're looking at a recipe and you want to find supermarkets close by that sell all of the ingredients for the recipe, and you want a sum of how much the recipe will cost. Yeah. Nobody is going to have that research done for you in your specific context. Yeah. So Google's not going to help you. Yeah. So not just niche things, but also things in a personalized context can be very difficult to solve on the web. Yeah. So these types of queries are hard on the current web because all of the answers we want are not on a single page. Yeah. If they were, Google would help us find that. On a side note, ChatGPT, I guess you've all heard, many of you are using ChatGPT. I haven't tried this query on ChatGPT. If somebody wants to try it at some stage, Nobel Prize winners who fought in a war, maybe it's very good, but I'm not sure. Yeah. However, there is a big question, and there is a lot of kind of debate in our research community about the effects of these large language models and how they connect with the topics of the course. So I have to give a talk about this eventually in a conference, but so we'll talk maybe a little bit later about that, about ChatGPT, but I don't think it's going to solve the sorts of issues that we saw. Yeah. But if somebody wanted to try that in ChatGPT, I'd be curious. I didn't try it yet. But see if that query could be solved. Okay, questions, doubts? Okay, so what's the problem? What's the key problem? Why is Google no good at this? Is Google just bad? Should we build another search engine? The problem is that the underlying kind of issue with the web is a fundamental issue. Yeah. So the current web is document-centric, which means that we have some pages. For example, we have a page here about Ireland, web page. And it's written in HTML, right? Hypertext markup language. So it looks sort of like XML if you know XML, or looks like HTML if you know HTML, because it is HTML. Within HTML, we have different tags that represent a structure of a document. So we have body tags here that represent that this is the content of the page. We have a H1 tag, which says this is a level 1 header. And then we have a div or a division for a flag. So we put an image in there with a source, we put in some paragraph, we put in another paragraph, we put in a link, and that link goes to some other web page. This is essentially at its core the web. Yeah. Now we've got a lot more fancy things, and we continue the documents. We've got some fancy things to make the pages look fancy and to load things asynchronously. We've got dynamic elements of web pages. We have user-generated contents and comments and so forth. But fundamentally, this is still the content of the web. Yeah. This is how the web is formulated. So most of this makes sense to humans. So if you see this as a person and you speak the language of the web page, you can read this and you can get some content from it. You can understand something. You can conceptualize it. Yeah. You can figure out that we're talking about some country and that there's some capital that has a certain population, for example. We can sort of project that into a real world meaning. And that capital is called Dublin. Yeah. And there's yes there. We might have some background information that we can also use to connect with what we've understood. And that's, of course, assuming that they speak the language. Yeah. So if they don't speak the language, then it might be a bit more difficult. The situation is even worse for machines because they don't speak our language. Yeah. So if we look at this from a machine perspective, what does this content look like? We remove all of the kind of semantic meaning, all of the language that we've learned, we've trained our brains with. Then the pages look like this. Yeah. So what have I done here? I've just basically mapped one letter to another letter. It's the same content. So essentially, I've just garbled all of the letters, but I've not garbled. Okay, here we have some bits that are images. It doesn't really make sense to us too much. And now the machine has to somehow, if it wanted to integrate data from these different web pages to do more complex tasks, it would have to try to understand what the hell these words and these things mean. Yeah. So this is not trivial for the machines to understand. Yeah. So when I say understand, I'll come back to that. I'm going to put that in quotes to emulate an understanding of. So here I left the domains the same because at least the machine has some idea that these are web domains. But in general, the content is opaque to the machines. It's difficult for the machines to work with. So what's the problem with this? What machines can do on the web currently, very efficiently, is fetch documents because they don't really need to understand what the content is. So they receive a request via HTTP for a particular URL, example.org/Ireland. The machine goes to the web server example.org. This other web server returns the page and it is displayed to the user. Yeah, this is what machines are very good at. Yeah, this is their core task on the web. Store documents, retrieve documents, display documents. They can also find documents, which is what Google does. Yeah, so somebody types in a search, Ireland. This in the machine view looks like some garbage. It doesn't really understand what it is, but it knows that it can go and search for this string in documents using inverted indexes, relevance ranking, page rank. There's all sorts of stuff behind that to give good results. But essentially it matches this string that it has no idea what it is. Finds it in a document and says, hey, this document could be relevant for the user. Yeah. And the user gets the web page back and it makes sense. She typed in Ireland and gets Ireland as a result in the search results. So what machines cannot do is combine sources, at least in a highly precise general way. Maybe in some sources, a number of websites, but not over the scale of the web. So this is just, it would require more understanding of the content to do this. Okay, so this is where the semantic web comes in, the content of this course. So what do we mean by machines that understand? And again, quotes. When I say understand or think or this sorts of stuff in machine, I mean really emulate an understanding of, appear to understand. Yeah. There's no good words for this for machines. You could say pseudo understand or pseudo whatever, pseudo think. But okay, so machines that understand the web. Yeah. So how are we going to build this, construct this sort of scenario? What we'd like is somehow for the machines and the humans to have a similar understanding of the content of the web. And that way the machines could do a lot more automatically for us on the web, if that were possible. Yeah. So when I say think and understand, there's this quote by Dijkstra, who you've heard of Dijkstra in the context of? Graphs, yeah, Dijkstra algorithm. So Dijkstra has this quote of the question of whether computers can think is like the question of whether submarines can swim, which is a pretty accurate, or I like the quote. So we can say that submarines can swim, but obviously they don't swim in the same way as animals or humans or fish do, yeah? So it's a similar thing. When I say think, it's sort of in air quotes. I'm not trying to make some philosophical statement that machines can think or not think or whatever. But they can emulate this sort of process. So precisely on that philosophical question, there is this philosopher, Searle, or I'm not sure where they were from. They had this thought experiment, John Searle. They had this experiment, which was this Chinese room. It's more a thought experiment, yeah? So maybe the not most politically correct example or thought experiment for these days. But the concept is that there is a person in a box and is receiving messages in Mandarin or in some Chinese alphabet that they don't understand. In the middle, they have a rule book. So they receive the rule book and they get some messages for this input symbol, you follow these rules and you produce a certain output. So this person in the middle has absolutely no idea of what the symbols mean or their semantic meaning. Yeah. And the question is, first of all, okay, well, let's imagine that the rule book was sufficiently detailed. It was sufficiently good, and this operator in the middle was sufficiently efficient in order to process the messages, such that the messages going out seem real. They seem like good responses. Yeah. Then the question is essentially, is this box, is this algorithm here, this operator, intelligent? Does it exhibit intelligence in terms of understanding the content? Yeah. And this is very much ChatGPT. This is very much what these large language models are doing. And the question then is this really a sign of intelligence or not? So that's a philosophical question. Yeah. There's not so much to say, but essentially this is similar to also what we want to implement in a different way on the semantic web. Yeah. What we'd like to do is to somehow be able to have this operator that can emulate this sort of an understanding of the content of the web. Yeah. Even if it doesn't really understand what's going on, it follows some rules and algorithms to emulate such an understanding. So that's very difficult to do in natural language, although with large language models, which is sort of, you know, I'm quite surprised by these language models, how good they are, large language models. But okay, so here, if we try to do it in natural language, we have essentially this sort of scenario where we have two web pages and we have an input question. Yeah. So we have this input question, which is nef us fi words foul up fi berofs up ogisel you. So what's the answer? So you have all of the information you need here, so it should be relatively easy. So this is what we would like machines to solve, yeah? Without any understanding of the content of these words, we just garbled the letters, which doesn't really change anything from a processing point of view, from a machine point of view. It's just an isomorphism of letters. We've not really changed the content, and this is very difficult. You have to receive in natural language a question and then respond to it. So the answer, of course, in this case, what should the output be? The answer in this case should, of course, be Uli Masoul. Yeah. Okay. So what do we? So obviously the machine is confused. This is a very difficult task to solve. So we'll come back to what that example was in a little bit. So why is it difficult for machines to understand? And here I use this orange color for somehow semantic or for human meaning, and the white part for machine meaning. So on the one hand, we can use in natural language multiple names for the same thing. Yeah. So we can have, for example, Ireland, IE, we can use a code, Irlanda, Republic of Ireland, Ada, whatever. So the user with sufficient knowledge about that would be able to know that all of these things, all of these names refer to the same thing, some country. Yeah. While the machine would be confused. It might think that these are four different things, reasonably, because the names are so different. Yeah, how is it going to know that these all refer to the same thing? And if you worked with data, you might have had this problem where you have two different data sets. They talk about the same thing, but using different names, and it's very difficult to align them. Yeah. So we can also have the case of multiple names for one thing. For one name for multiple things. So we can have, for example, Dublin, which is capital of Ireland, or we can have Dublin, which is an Irish bar in Bella Vista. Yeah, so we have the same thing. It refers to two different entities. Yeah. So in this case, of course, the machine might think that there's only one thing, that they're the same. Yeah, when they're not. Multiple ways to say the same thing. So, for example, we can say Dublin's population is 1 million. Dublin has a population of 1 million. Dublin's population is 1 million. Dublin has 1 million inhabitants. 1 million people live in Dublin. Its population, Dublin, blah, 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 blah. Its population is 1 million. La población de Dublin es 1 millón. Or, okay, we can say it many more different ways, right? So the machine is getting a bit sad at this point. It's starting to realize the challenge of its task. And we can have multiple meanings for the same saying. So we have this classic phrase that's used in natural language processing in English. Sherlock saw the man using binoculars. I don't know if you know binoculars. I don't know these sorts of things for seeing far. I don't know what they're called in Spanish. But binoculares. Yeah, okay, that's easy. I don't have to explain that one. So okay, fine. So the user, okay, so there's various ways of understanding this, even from a human perspective, right? So Sherlock saw the man using binoculars. Do you see the two meanings? Sherlock saw the man using Sherlock's binoculars, or Sherlock saw the man right there, and that man was using binoculars. Yeah, so it's not really clear what the ambiguity would be here. So there's this possibility. Sherlock was the one using the binoculars, or Sherlock, the man that Sherlock saw was the one using binoculars. Yeah. So the machine's getting even more sad now. And okay, the machine sees this other phrase, this one in Spanish, or in Chilean, I suppose. Fred está arriba la pelota. and thinks the machine knows this one. The machine's quite happy because it thinks that Fred is on the ball. But that's not the case. So this is tricky for the machine. Yeah, so it's difficult for the machine to work with natural language. There's a lot of subtlety, a lot of intricacies with natural language. So the machine is sad again. So this is often referred to as the semantic gap. Somehow this idea that the machines, they can't go to a bar and get drunk. They can't drink lemonade on a hot day. They don't experience the world in the same way we do. And for that reason, they won't experience somehow, they won't be able to understand content in the same way we do. However, they can learn from us. Yeah, as ChatGPT is doing, they can somehow emulate an understanding. So the question then is, what if, like in Cyril's room, we could structure everything? Yeah. So what if we could, for example, have one symbol with one meaning, which means that instead of having 5 different names for the same thing, we have one symbol. Yeah, whatever that symbol is, doesn't matter. It's just something we all agree on. This means this country. Yeah. What if we had, again, one symbol, one meaning, which means that we can't use one symbol to refer to multiple things. We remove this problem. Idealized world. We're never going to be able to do this idealized world, but okay, let's just assume we could. Yeah. That would be great. Okay. What if there was one simple way to say one thing? So rather than having all of this sort of redundant subtleties in natural language, we simplify the statements. And we say something like a subject, predicate, object type structure. So Dublin, population 1 million. Yeah, and we just remove all of the different nuances to natural language. So in this case, then in the machine, we will use symbols. So we'll use these unique symbols that just refer to one thing. Yeah, so we can make statements like this. So this was the example we saw before in natural language where the machine struggled to understand. And what okay, so I'll explain the example. I think I have that soon. So what the example is asking is, what is the population of the capital of Ireland? And this says 1 million. Yeah. So what if we were to actually structure the web based on what we just saw? So what we're going to do is we're going to use one symbol for one thing, and we're going to use what's called a symbolic approach. Yeah. So there's sort of neural approaches, which is machine learning, and then there's symbolic approaches, which are classical logic type approaches. Yeah. Or also databases, for example, SQL uses this approach. So what are we doing? We're representing knowledge using symbols, which is just using one symbol to refer to one thing. And we have some sort of structure for that. Yeah. So what we have here are triples of symbols. We're representing more or less the same information we saw originally. Yeah. So we have this data here, which has 3 triples, and we have this data here, which has 2 triples coming from different websites. Our question now is this question here, where we have X and Y represent variables. And we need to create an answer for that. Yeah. What I'm going to try to argue is that this is a lot easier for a machine. So we have this strange H symbol here. Does anyone know astrology? Any people who are experts on astrology? If you were experts on astrology, you would recognize these symbols. So if you recognize the symbols, the idea is you're not supposed to. They're supposed to be opaque symbols. Yeah. So we have this weird H here, and then we have 2 dots connected with a bar, with a line. Yeah. So what do we think could be a possible match for X? So we look here, we have the H, but we don't have the 2 dots. We have the H, but we don't have the 2 dots. We have the H and we have the 2 dots. That seems promising. So this seems to match here. This seems to match here. So then we could say that this X would be probably Neptune. I don't know, this thing with the fork. Yeah. So we'll say, okay, if X is the fork, then now we're trying to match this thing here. So we're looking for X, where X is a fork. We're looking for this circle with a line. And we're looking for Y. So what could Y be? So we look here, these are all weird H's, weird H, and then we say, okay, so actually the fork is in the right position. We have the circle with the line. So we think Y could be this number here. And I've left the number as it is because it doesn't make sense to replace numbers or data types like Booleans with symbols, because the machine can process their value. It can say one is less than the other. It can add them. It can subtract them. It can do different operations. So we're not going to represent those things with symbols. So what should the output be? The output should be something like X maps to fork and Y maps to 1 million. Yeah. So we could see that we could do an algorithm. We can make an algorithm for this. This is essentially doing an SQL query or something similar. Yeah. So in this case, the machine is happy. The data is in a structured format. The questions are in a structured format. The output is structured, and everything is exactly what the machine is good at doing. It can solve this relatively efficiently. So what are we doing in the human world? Well, we have our three triples here: Ireland, part of Europe, Ireland as a country, Ireland capital Dublin, Ireland capital Dublin, Dublin population 1 million. And our question is Ireland capital X, X population Y. Yeah. So we're asking what is the population of the capital of Ireland. Our result comes back, X is Dublin, the capital, and Y is 1 million. Okay. So we have another question here. This time we have a simpler, what looks like at first a simpler question, which is we have X with a circle and a dot inside and Y. So what would X be? So that weird H thing here. And then we match this circle with the dot. I don't know, Jupiter or Mercury or something, I don't know. And Y to, I guess, the goat thing, the Aries. And the output should be as follows. Yeah, so we get X maps to this weird H and Y to this the symbol for whatever it is. We don't know. Yeah. So in the humans, if we understand this from a human perspective, it looks like what we've asked the machine is X part of Y, and then we get X maps to Ireland and Y maps to Europe. However, if we look at this from a human perspective, if we look at these data, we could probably come up with more answers than this. We're missing some answers, right? So what answers are we missing? So we're asking X part of Y. So we want X to be part of Y, and we want all of the answers possible from these data here. Yeah. So what we've got here is Ireland part of Europe. Yep, that's stated explicitly. So that one's easy for the machine. What other cases might be of relevance if you were to think about these data? What other answers might the user expect? For example, we have Ireland capital of Dublin. Would that not imply that Dublin is part of Ireland? Yeah. And there's a third answer. Anybody see the third answer?
Dublin is part of Europe.
Yeah. So we have a transitive property, right? Because if X is part of Y and Y is part of Z, then X must be part of Z. Yeah. So we have a transitive property as well. So if we apply reasoning or logical deduction to this, based on our understanding of this, we could also say, hey, but you're missing answers here. What about Dublin, Ireland, and Dublin, Europe? So we could expect Dublin, Ireland, and Dublin, Europe. Yeah. So what should the output be? In this case, what we're going to do to try to get these extra results is to add some rules. We're going to add some logical rules. Yeah. These are called horn clauses, or essentially we can write them in first order logic. We don't need all of first order logic, but we can write some stuff, some logical statements. What we say in this case is if B has this symbol with A, then what we want to infer is that A has this circle symbol with B. Yeah. So what will the output be in this case? Well, we can take in this case this weird H with the two dots here connected and the A. Yeah. And then we can say if this is the case, then it should apply that we swap the direction and we put a circle with a dot in there. Yeah. So what are we doing really? That allows us to get an extra result. So what we're doing is essentially we're saying that if B is the capital of A, or B, if B has capital A, then A is part of B. This is the rule we're applying. Yeah. So we state this once, and now we can use this rule across the web. Yeah, if we trust this rule. So when we go to ask the question, X part of Y, now we get an additional response because we have this rule. We have this extra information that we can use for logical deduction. So now we get the rule, we get the new response. that X can map to Dublin and Y to Ireland based on this rule. Gives us some extra answers. What about the Dublin Europe case? For the Dublin Europe case, we can add a new rule, and this is the transitivity rule. Yeah, so A circle B, B circle C implies A circle C. Yeah, so A part of B, B part of C implies A part of C. Yeah, so now we get a third answer to our query. Yeah. And we can think about how to implement this using algorithms and logic. Yeah, so now we get our third response, Dublin Europe. So this is the core of the semantic web. This is essentially the topic, and we're going to look at specific formats and data structures and techniques and algorithms and problems and decidability and undecidability and all sorts of issues relating to this. So this is the core proposal of the semantic web, that instead of just publishing documents for humans to read, we're going to also publish data. Yeah. So by that, I mean triples, this sort of format here, which corresponds to a graph. Yeah, it corresponds to a graph structure. Some of you might have seen RDF before. We're going to talk about logic, and we're going to talk about rules and ontologies, way to represent knowledge. So how do we define things? How do we define things so machines can reason about them? How do we define what a book is? Does a book have pages? Are they physical pages? Does it have a price? What if there are different copies of the book in different places? Yeah. If I say something is my book, does it mean I wrote it or I own it? I bought it. This sort of stuff. So this is the logic. Then we have the query layer, which is Sparkle, which you might have seen before. If you did databases with me, for example, you might have briefly seen Sparkle, or maybe you skipped it because it was the last lab and you didn't need the grade. But we'll see Sparkle in more detail in this course. And then you have your output, yeah. So you have some results returned. So this is the core idea of the semantic web. So I'm going to talk a little bit about the semantic web now. Has anyone questions or doubts? Comments? Okay. Okay. So the semantic web has been around for about 20 years, a bit longer. 2001 was the kind of publication of this article that outlined the vision, but there was work before that as well. So 22 years. So if it's been around for 22 years, why have we not heard of it? Yeah, is it a complete failure? Is it a terrible idea and nobody's using it? And well, so what's going on? Where is it now? It's a very reasonable question to ask. So where is it if it's been around for 20 years and we're still not using the semantic web, we're still using the regular old web? So the point is that you are using the semantic web. The semantic web is not a different web. The semantic web is just putting semantics or meaning or content or structure on the current web. Yeah. So it's more like an evolution of the current web. And it's also something that's not really user facing. So it's not like there was this web 2.0. I remember when I was working in the semantic web area, the semantic web, they called it web 2.0. And then all this user generated content stuff came, and that was web 2.0. So then we said web 3.0. And now people are using web 3.0 for some other thing, which is, I don't know, IoT or Bitcoin or blockchain or something, I don't know. So that's 4.0, web 4.0. But really, in general, the semantic web you're using already. It's hidden within the web. It's not something you may notice, yeah? But it has subtle things that you will, if I point them out, hopefully you'll say, oh yeah, okay, I am using the semantic web. Well, let's see. So one thing, okay, we'll come to one thing that everybody's using. Not everybody's using Wikidata, but it's my favorite project relating to the semantic web. So I work a lot in this area. I do some research on Wikidata. I supervise students who work in Wikidata. So we have various, I'm very interested in this project. So Wikidata is a Wikipedia for data. You might have seen maybe an introduction. I talk about this as well in databases, but some of you may not have seen it. So it is essentially, what is Wikidata? Think about Wikipedia, but data. Yeah, that's pretty much it. You can edit things, you can add facts, you can add information about different types of entities. It currently has surpassed, I think this is slightly old, but it has surpassed 100 million items. Yeah, so items or entities can be any sorts of things. It could be recipes, it can be countries, it can be movies, it can be people, it can be papers, it can be whatever. It has a vast amount of entities described. So roughly speaking, a Wikipedia for data. Why? Why would we bother doing that? What's the point? Yeah. So Wikipedia has various problems. Wikipedia, if we think about editing Wikipedia, we have these info boxes in Wikipedia. Yeah. These are data boxes that are in the top right corner. And this is about, I guess, a familiar face for many of you, Alexis Sanchez. Yeah. So what we have here are info boxes in different languages. This one's in English, this one is in Spanish, and this one is in German. Yep. So can anyone see any problem? I know it's probably small to see this from the back. Can anyone see a potential issue?
There's different information in every.
Yeah. So in general, so the way I've cut the data is sort of a bit arbitrary, but you see that the information looks different, right? There's even a key issue here, which is that the number of goals for Chile says 76 here, and these were taken at the same time. Now out of date, but these were taken on at the same time. And it states that Alexi has 82 goals, and 82 goals in English and in Spanish, but in German it says 76 goals. Why does it say 76 goals in German? Do the Germans not like Alexis Sanchez? Yeah, it's not been updated. And why has it not been updated? Because the Germans don't like Alexis Sanchez. So they're not so interested in Alexis Sanchez. Yeah. So this has to be manually updated every time Alexis Sanchez scores a goal. So somebody has to go in there and edit that information. Yeah. So you can see that this is already kind of stupid. So this is not a good way to go, right? Not only do we have this information redundantly across different languages that needs to be synchronized manually by users, but we also have this information replicated in lots of different locations. So there might be a table of the scorers. How many goals has every Chilean player scored? In another article, there might be a table for the top scorers of that tournament. There might be a table for the whatever the top scorers of all time in international football. So a single goal scored by Alexis Sanchez, for example, means that afterwards, this army of editors needs to go out and edit hundreds of different places in Wikipedia, potentially, to keep it up to date. Yeah, which essentially they're just not going to do. So this is an issue. So now after this goal is scored, this means that an army of human editors has to manually update a bunch of articles in different languages, lists, tables, whatever it might be in Wikipedia. Yeah, this is not something that makes a whole lot of sense for, let's say, 2023. So inevitably, there will be data that will be out of date in different languages or different tables. So the solution to this problem is to manage the data, the structured data of these Wikimedia projects like Wikipedia in one central location and in a way that's agnostic to languages. So, and also to make this machine readable. So it uses some semantic web stuff that we'll see later in the course, RDF, Sparkle, and so forth. So we have this sort of semantic web version of Wikipedia, which is very interesting. So we can log in and we can get a description of an entity, for example, in this case, Alexis Sanchez, and we get some, rather than some text that we would understand natural language, we get some facts. We get a list of facts about this entity. Yeah? Gender, member of sports team, since when, what dates, where they were born, where they died, if applicable, and so forth. Yeah? Not just for people, but also for football teams. For, as we see here, these are also entities. We click on one of these, we get that view of that entity. Yeah, and this forms a graph. Not only in English, we can also just switch to Spanish and we see exactly the same information, the same data. The data don't change in the, well, there are debates about that. In French, for example, they have a notion of male and female that applies to animals distinctly from people. And they do not want to use the same concept of gender. So there are, of course, some differences between different languages. In this case, we have Spanish, so there's no such complications. We just translate the labels here, and we get the labels in Spanish. The data don't change. If we update the information in one language, it spreads to, if we update in English, it spreads to Spanish and so forth. We have, German. This is the German information. We have, I guess, some Cyrillic, Russian. I don't remember, to be honest. Some Cyrillic-based language. Definitely don't remember what that language was. Anybody know? It's some Southeast Asian language. Not sure I remember, but yeah, we also have it in this language, which is cool. One thing that's worth mentioning here is what's interesting about this case is we don't have a translation in this language of member of sports team. So what this says is the label in English, and then it says English here. So I don't know actually how you could even find out what language that is without looking through lots of different languages. I don't know how you can search that, but yeah, so we have Wikidata in all sorts of different natural languages. What does it describe? And this is again a little bit out of date. Actually, this is up to 100 million now. It has about 23,000 unique active users. They would be people logging in every month and editing or changing something. And it has, according to entities, the types of entities it has, lots of people, lots of taxons or species, lots of administrative territorial entities, which are places or towns or regions, architectural structures, buildings, universities, libraries, and so forth. Occurrences, which are events, some assassinations, some war, some whatever. Chemical compounds, movies, thoroughfares, which are streets, astronomical objects, which are stars, planets, supernova, galaxies, and so forth. So it has a wide range of entities. Specific use cases. So already more and more in Wikipedia, when you look at these info boxes here, what you're seeing is actually something created by Wikidata. That data is managed by Wikidata, yeah? Not in all entities, but essentially for different types of entities, they are releasing more and more the use of Wikidata for this. So if you try to edit this Atacama Pathfinder experiment, for example, if you try to edit this info box, you'll see that you no longer have markup in the Wikipedia page. Rather, it redirects you to Wikidata to update the information. And once you update the information on Wikidata, it should propagate to all of the language versions that support the same view of the info box. Yeah. So if you're using Wikipedia, you can check this out, and sometimes, not always, but sometimes you'll see this edit on Wikidata feature. Yeah. So this is to address this Alexis Sanchez problem that we saw earlier. Yeah, so you click here to edit, and really what you're going to be doing is editing Wikidata directly. It's also very useful for doing quality checks, yeah. So which is something very difficult to do on Wikipedia. So here, for example, we have a query where we're looking for people who do not have an age between 0 and 130. Yeah. So we're looking for cases where, for some reason, the age might be out of date, or the age might be incorrect. Or maybe the death date has been incorrectly stated, or the birth date has been incorrectly stated. So we see some results here. The first result is Tukti Yusupova, okay? And it states that their age would have been 134 when they died, which is kind of reasonable, maybe. I don't know. Could be possible. There's a Kanni Mata who lived to 150, apparently. Okay, this was in 1387 to 1538. So how reliable is that one? Okay, could have been. We have a no label who lived till 207. We have Chenjun who lived 443 years. We have Salah, who lived 433 years. So we might have some doubts about this, about the quality of these. We might want to go and check. And we can automatically extract this via a query, right? However, in Wikidata, we can also represent information about mythological entities or about religious figures, for example. So there might be arguments to say that actually these are not so strange, these cases. There might be valid reasons why somebody would live to 443, yeah, in some mythology or some religion or whatever it might be. What would be more difficult to argue, however, is why there are people with negative ages. So here we have people who are minus 45, minus 34, Max Halliger, minus 1, minus 330, minus 322, Johann Ehrenberg. So in these cases, we could probably think there's probably some data issue going on here. Yeah. So an interesting thing about having data in a structured format as well is that Wikidata can provide a query service for querying the data. So this query service uses, let me see something. I'm going to stop share. Let's see. Sorry, I'm going to switch the share to, hopefully there's nothing. Yeah, should be fine. So we can use this query service in Wikidata to query the Wikidata query service. So we can write structured queries against Wikidata that will be answered over the entire collection or graph of Wikidata. So what I have here is a query that is looking for Nobel Prize winners, winners of Nobel Prizes in literature, the date of the award, the year of the award, what wars they fought in, the name of the war, and then we're looking for information in English. So essentially, we're trying to resolve this question we saw earlier in the class. So we're going to run this query. It's kind of a little bit complex, but anybody can go and run queries there. And what we get from Wikidata's query service is a list of the different wars, the Nobel Prize winners in literature, the wars they fought in, and the years of the war. So we get Solipodrum, Henrik Steinkiewicz, I don't know, Carl Spittler, Winston Churchill. It's kind of a strange one, but he won a Nobel Prize for his oratory, for his speeches. Ernest Hemingway, Albert Camus, Jean-Paul Sartre, Mikhail Chokolov, Samuel Beckett, and more. Yeah, William Golding and so forth. So we get some answers. These may not be complete answers, but we get some answers that we can work with. Why might we not have all of the data? Because like Wikipedia, Wikidata is not complete. It's edited by users. So it might be missing information, but you can always go and add that information if you find something more. So that's the Wikidata query service. So we get these answers that we saw here. Oh, sorry. I need to share my screen again. So we know that it's also used in other applications. So for example, if people have used Siri or Alexa, we don't really know what data sources Siri, Alexa, and these sorts of things use. Companies like Apple and Amazon don't reveal this information very openly. However, we can be almost certain that Siri uses Wikidata. And the reason why we can be almost certain is that before Stan Lee had died, Siri started telling people that he was dead. He was still alive, and Siri started telling people he was dead. People started to investigate why that might be, and they found that somebody had edited, a user called Beer and Love, had edited the wiki data profile for Stan Lee to add a date of death of that day. And almost around the time of that edit, Siri started telling people that he had died. Yeah, so for that reason, although we don't have any official information about this, we can be relatively sure that Siri uses Wikidata. So yeah, so this is the discussion of that, where this Beer and Love user suspiciously around the time Siri starts reporting his death, edits the information in Wikidata. Another kind of maybe even more common use case where people have been using the semantic web would be through Google. Yeah. So Google has been building what it calls its Google Knowledge Graph. And the whole concept of Google is that prior, let's say, until maybe 2009, 2010, Google was strictly an information retrieval engine. It would take strings, it would look for strings in documents and indexes and return things. Around that time, Google wanted to become more semantic search. Yeah. This means that, for example, a search like Suliculum would be not just a string, but it would be recognized as an entity. Yeah, that this is an author, that this is a person who wrote something. So around this time, it started to try to identify somehow what the entity would be. Yeah, that this is an author. And this is when the knowledge panel started. I think this was around 2012, 2013. This started to be published. So it would recognize that this is an entity, and it would provide a panel here with some knowledge or information or data about the entity being searched for. So this is sort of a move as well towards somehow a semantic web, recognizing, you know, the semantics that there are these entities and so forth. So now Google has moved from, it had its own knowledge graph, something similar to Wikidata. It decided to abandon its knowledge graph and migrated to Wikidata because they don't want to be the truth sayers of knowledge. They don't want to have anything to do with saying what's true or what's false. Yeah, they want to leave that to users. So they bought this company called Meta, which had this knowledge graph, this collection of data similar to Wikidata called Freebase. And then Google proposed that Freebase be integrated into Wikidata and Freebase be abandoned. Yeah. So another type of application where you will see semantic web light in Google is rich snippets. So if you don't know what rich snippets are, you've probably all seen them. It would be almost impossible to avoid them, unless you don't use Google ever, maybe. But even in other search engines, they also appear. If you search for something like lemon meringue, lemon recipe, you'll get some search results like this. Yeah. And you'll see that these search results have images, they have ratings, they have here a point rating 4.6, number of reviews, 1,600 reviews. It has 40 minutes and it has 298 calories. How does Google know this information? This is data, metadata it has about that result. So how does Google know this information? Any ideas? Yeah, it's in the document. Yeah. So one of the big arguments are people who were against the semantic web at the start. They're saying this will never happen. They were like, well, why would people structure their content? Who's gonna structure their content? For what reason are they going to do that? So how does this thing get started, right? So one of the most successful use cases has been this rich snippets idea, where Google wants to display something more than just the title of a page and some paragraph of the text. Yeah, what they'd like to do is have these enriched search results that have some image, rating, calories, reviews, and that can also change by the type. So if it were a movie, you would rather maybe display an image with the director and a rating and something else. If it were a book, it would display other type of information. So the search engines wanted this type of rich snippet. And what did they say? They said, okay, well, we're not going to try to extract this. That would be too difficult. We're just going to say, if you add structured data to your web page, we're going to give this nice looking result. And a nice looking result means that users are more likely to click. Yeah, so it's sort of a win-win for everybody. Yeah. So the search engine wins because now it has these nice looking results. The websites win so long as they structure their content and add metadata, because now they have a nicer looking result with more clicks. And the users are happy because they get more information to choose between the different search results. Yeah. So this is using formats such as RDFA, JSON-LD, which come from the semantic web. So how does Google know the ratings, minutes, and calories? People have actually embedded the data into their web page, and there's various ways to do that. Yeah, so already there's this idea of web of data, right? This adding structured data into things and the applications that arises. Publishers get more clicks on the results, and Google gets data to make fancy results. So this is a direct kind of a response to critics who say, why would you structure your data? This is an example of the value for that. Yeah.
But if the data is like embedded itself in the document, but you cannot query that documents, that collection of documents, like in a systematic way.
You can kind of do that because there are certain vocabularies, there's a certain structure to this. So Google needs to have a certain vocabulary or set of terms or ways to understand the data. So together with Google and together with a bunch of other web search engines, they decided rather than having a Facebook format and a Bing format and a Google format, that they would create a sort of an industry standard. And that's called schema.org. And in schema.org, they define what the different types are, what the properties can be of those different types. So you could say, okay, there's movies, there's different types of movies. You can have a rental price for a movie, you can have a director for a movie. So it defines a vocabulary that puts a bit of structure on this. So it's not just like every website is different. What is missing are the symbols for entities. So within IMDb, for example, you'll find the structured data, but the IMDb link will be, or URL for something will be different than the one on another website, like Rotten Tomatoes. They don't correspond, but the vocabulary used, at least there's some standard there. So you could integrate it and you could query it.
But there is no like an endpoint.
No, what you would need in that case is a search engine. So you need something that could actually go out and crawl this data, extract it. And I also worked on one of these for a while, but there is no use cases. They're very expensive, and it's very hard to maintain those things if you don't have revenue, because you need a lot of machinery and so forth.
So currently, there is no endpoint for querying like in Spark for the web.
No.
To query that web.
No, still no. And there's a lot of work on how to do that. So there's a lot of different projects that go in that direction, and there have been projects that try to do that try to index all of this RDF data or the structured data from the web. But they were mainly academic. I was involved with one of them, and they're very expensive to keep going without an actual use case. So they were more like prototypes. There's also data sets like Web Data Commons, where people crawl or they extract from Common Crawl. From these crawls of the web, they extract this RDF data. So you can get your hands on that sort of data of products and movies and whatever. It's called Web Data Commons. It's like a dump, but it would be a little bit out of date.
But is there any standard for maybe like a pin from the document to like a central server or something?
That all existed, yeah, and that all fell away because it was too expensive to. We had all those services running at one stage in the research where I did my PhD. We had there was Ping the Semantic Web was that service, and there was Syniche and Swizzy and all sorts of search engines. So I think it would be an interesting time to bring that back, because there's been a resurgence in interest in this, but you need to somehow commercialize it or have a lot of funding, because you need a lot of machinery to do this sort of thing. So it's not trivial. The technical side is not that difficult. The difficult part is funding the machines and the things that you need.
Or maybe a federated system of computer. So no federated services are like gaining some like they're like federated social networks now, like Mastodon.
Yeah, and the semantic web is involved in those things as well. So there's pushes towards federation. There's a lot of people who worked on federated querying. So we saw the Wikidata query service. And the idea then is, okay, are we going to put everything into Wikidata? It doesn't seem reasonable. So probably we're going to have different websites with different query services. That query language supports federation. So you can actually query other similar services on the web, get those results, and join them with Wikidata to do something more.
For example, from Wikidata, I can like query geontology or something.
Yeah, exactly. Yeah. So the query language supports that. We'll see some examples of that later in Sparkle. There's also work on how to find data, navigate data at runtime. So it's sort of, you do a small crawl just to answer a question. So you don't need any query services. You just kind of follow links to try to answer one particular question. So there's a lot of work in that direction. And there's also work towards federated social, there's platforms, a project called Solid. So there's research in those areas, but they're all kind of prototypes still. And federation is not easy, it's costly. It's hard to optimize because you don't know the statistics of the data on the other side. So yeah, there's working. More questions? Thoughts? No? Okay. Another use case for the semantic web is structured is linked open data or linking open data. So the idea is that there's a push towards transparency. 2 weeks ago, or 3 weeks ago, or 4 weeks ago, I went to La Moneda, because the government wants to not La Moneda like but somewhere in La Moneda, another building in La Moneda. The government wants to create an open data platform. So there's some political capital or urgency to do this because they want to increase certain metrics for transparency. So they're like, okay, we should have an open data platform, and there's some political will behind that because some number will go up in transparency for the country, and that will look good. So they were like, okay, we're going to do an open data platform. And then there was a discussion. It's like, well, we already have an open data platform. So 5 years ago, the same thing had happened, and they decided to make an open data platform. They created the open data platform. They put some data in there. They did a good job. And then everybody celebrated, took some photos, and then everybody forgot about it. And all of the data disappeared and went out of date and so forth. So now they're thinking about the same thing again. Yeah. The point in general is that there's this push towards transparency and open data, to be able to make social data available for social good. And this is a very promising initiative, that somehow data can be used for innovation, for business, for decision making, for transparency, for understanding why decisions are made and so forth. Not just in governments, but also in science. So there's a big problem in science, which is reproducibility, where papers are published and nobody can reproduce or nobody can regenerate those results because all of the stuff doesn't exist anymore. The data sets are not available, the code's not available, and so forth. So there's a big push towards open data for science as well. Of course, not all scientific data can be made open. There's a lot of sensitive data and so forth, but where it can be made open, why not publish it? So in various parts of society, there's a push towards open data, and there's a big question of how to publish open data. Yeah, so maybe you've seen like websites like Kaggle, where you go in and you download a data set, but the data sets are all in different formats. There's no links between them. You don't understand what the columns mean. It's a disaster sometimes, right? And we still haven't really solved this issue, but in the semantic web, there is a specific proposal called the 5 stars of linked open data. And the idea is that every star is great. It's just great to have data open, no matter what the story is. But every step is better. Yeah. So the first step is to avoid PDFs. So for example, if you have a table, don't put an image or a scan of a table that's slightly sideways and black in the corners and publish that as your data. Yeah. Why? Because it's going to be super difficult to read the data or open the data in any sort of application. So a second option is to have Excel. An Excel worksheet would be better, right? An Excel spreadsheet. So an Excel spreadsheet would be better than a weird image of a table in a PDF that's slightly skewed. But it's still not great. Why is it not great? Because it's Excel. Yeah, who wants to parse an Excel spreadsheet? The first thing you're going to do if you get data in an Excel spreadsheet would be to open it in Excel or some version and export it to CSV or some other reasonable format. Yeah, and then you're just probably never going to touch the Excel again. You're going to take the CSV and you're going to open it in Python and work with it. Yeah. So this is why CSV is considered better, because it's non-proprietary formats. It's easier to work with different tools. Yeah, you don't need to open it in some spreadsheet software to be able to read it. So CSV would be considered better because it's open structured format, machine readable format. Next we have RDF, which is something we'll see. Yeah.
I don't think it's totally correct because back in the day, Excel was a proprietary format, but now you use it like an open document thing, like Excel SX. Yeah. So I think Excel files or open document files are better than CSV because they are like typed columns. Because if I have a number column or a date column, I can type that column in open document format. Yep. So I can parse it like better than CSV. Yep. CSV is also a standard, like again, RFC standard.
Yeah. Okay. So there's 2 points there. So the first, you say XLS is not proprietary; it's an open format.
XLS is proprietary, but now they are using XLS X.
XLS X.
Open document format. It's open. It's an open.
Yeah, you can open it using different tools and so forth. So yep, and then your point as well is if you export XLS to CSV, you lose information. Yeah. which is fine. So I guess in that case, you know, you could save it as XLS and you could save it as CSV alongside. But the point here is that it would be great to have some format. Okay, it would be actually ideal to have a format that loses no information relative to the XLS. And that's easy to parse without like having to import libraries or specialized tools and so forth. Yeah, but they're valid points. Yeah. So moving from so I guess the key point is non-proprietary and easy to parse. Yeah, so if it's non-proprietary, XLSX should be okay. Then moving to CSV. So from CSV, we have this weird jump to RDF, which is a conceptual leap. And the whole idea of RDF here is that we're going to identify things. We're not just going to put a bunch of strings in a column and then we're done. We're going to try to create or add identifiers. For example, instead of putting Dublin in a spreadsheet or Santiago, better example, Santiago in a spreadsheet with a column of city, we're going to try to put an ID. And what ID would we put? We could put, for example, the Wikidata ID. We could try to put some web identifier where you click on that, it's a link and it brings you to what that thing is. Yeah. So that's a jump for RDF, which is also a graph-based format. And then linking open data is this idea of linking to other things on the web, which I just mentioned. So it's this idea of linking to Wikidata, and that gives you context for what this entity is. So these 5 steps are the 5 steps of linking open data. The last 2 are the most costly. But there's been quite some success in getting this scheme or proposing this as a way for people to structure their open data. But this has led to something called the Linked Data Cloud, where there's a bunch of organizations from governmental organizations, US government, UK government, different media outlets, different scientific organizations. I'm not sure if NASA you consider engineering or science or what kind of organization it is, space exploration, different companies and so forth. Yeah, so there's been a bunch of organizations interested in using the semantic web for this because they're motivated to publish open data and they don't know how to do that. Yeah. So, okay, so that's essentially the semantic web. Introduction. So about the course, we're going to talk a little bit more about the elements of the course. The topics, main 6 topics we're going to cover. We're going to cover, first of all, data, the RDF data model, triple-based data model, which is thought of for the semantic web. It's a specific web-based data format. We're going to talk about knowledge representation. We're going to talk about ontologies. We're going to talk about automated reasoning for defining things like what is a bottle, what can it contain, what is a screen, what is a class, what is a course, what is a university, how to reason about those things. So a mix of logic and knowledge representation and different topics there. So we'll talk about 3 weeks of that. Next, we're going to have Sparkle, 2 weeks of talking about the query language. Briefly, we see it in databases, but we go into a lot more detail. We'll cover the full language in this course. Then we're going to talk a little bit about how to put all these things on the web in terms of linked data and web of data concepts. We're going to look at RDB to RDF, optionally, if there's time. It depends. So sometimes I publish that just as an extra video. Sometimes we've covered it. And we're going to talk about validating RDF data using shapes. This is a research course. So this is a postgrad course. This is CC7 something. So I think it's very important at the start to point out that this is not like a database course where these things have been around since the 80s and 90s and so forth, and everybody knows there's some standard curriculum or whatever. This is very much a research course in the sense that it's a research topic that's being covered. It means that we don't have all the answers. There are things we don't know. There are things that could be done better. There are things that could be done worse. Yeah. In terms of research, it means basically that the topics are a bit more open. And there's a lot more space for ideas and for discussion and so forth. It's not some settled topic that or some established technology that we're going to be discussing here, or some established theory. In that sense as well, given that it's a research course, there will be certain elements where we're going to get into more research level topics. I would say particularly around this part here. The other parts are not so research level, but there's going to be some stuff here that would be kind of getting a little bit more advanced. Another element of the course that is specific for research is there will be a reading group. So you'll have to select a research paper relevant to the course as a group and prepare a presentation about that paper. And the idea then is we'll share some talks so that you can see the presentations of other groups and understand a little bit about what kinds of stuff is being done by the research community related to this. At the same time, there's no need to be intimidated by this if you're coming out of a database course, if you're in third year, fourth year, or whatever. There's nothing super difficult about this. It's just the nature of the course is a little bit different to other courses. So each week we will have a class on Monday, like this class, to learn some concepts. We'll have a lab on Wednesday, and there will be an auxiliary session on Friday. So my long-term auxiliary has left, Jaime Salas. He's now doing a postdoc in Europe. So I don't have an auxiliary at the moment, but we'll see. But this Friday it probably won't be because I don't think it's necessary. But hopefully, starting next week there will be an auxiliary session. So the marking structure would be 70% labs, 20% project, and 10% reading group. We're not going to have controls or exams. For the labs, one key important thing is that to work as a you can work in groups, but to work as a group you have to come to the lab. Yeah, so you have to come in person. If you don't come, you can still do it alone. We'll publish some of the rules of the labs a little bit later. Yeah, so there's a book. I wrote a book on this topic. I'll be uploading this as a PDF if you want to read more. I'm not going to cover all of the content on this, but Springer published it and they charged a fortune for the book. So I'll publish a PDF and you can have a look at that. Outcomes, learn about the semantic web. It's an ongoing research topic in the BCC. So there are various professors working on that. One of them left, Jorge Perez, but myself and Claudio Gutierrez are working on that, and sometimes other professors as well are collaborating on that topic. I think there's also people in Industria that are working on this topic, so not just the DSSA, but also on the faculty. Apply some database logic, artificial intelligence, etc. to the web. Mainly when I talk about artificial intelligence, I talk about the old school artificial intelligence, not the new shovel a bunch of data into a GPU and create some large language model. I'm talking about logic and expert systems and so forth, which are not so popular. Mix of theory and practical exercises. So there's going to be some theoretical aspects, but they're kind of more one or two classes about knowledge representation and computational limits. Yeah, it's not a super theoretical course, I would say. So we will have practical exercises through the labs, and hopefully as well we can kind of discuss this general question. Maybe you come up with a completely different solution. Maybe your perspective at the end is this is a research course, is the semantic web stuff is never going to happen, it's a waste of time. But maybe you think, oh, this is something interesting, or there's something there. Maybe this is not the solution, but something else is. Yeah, so that's part of the purpose. I'm not saying this is the way things should be, but to get you thinking about these sorts of things. Yeah, and if you come out with a very strong, opinion that this is not the right way, that's perfect. Yeah, that's it's part of the research area. So questions? Any doubts or questions about the topic? Yeah. Yeah, we'll have a lab on Wednesday. It's going to be an informal lab. It's going to be more to motivate the course. You can just come, bring your laptops if you can. I'll try to get laptops, but it's been very difficult to get them in the past few semesters. So if you can bring your laptops, that would be great. You can work in groups of 3. And it'll be an informal lab. You don't really need to do any prep or anything. It'll be more to motivate the course. So there will be a lab on Wednesday. An auxiliary, I'm not too sure, probably not. More questions? Yep.
Can we just define some labs?
So you can miss 2 of the labs. I have to count. I don't remember how many labs are in total, but there's about 11 or 12. It depends on whether we do as well the RDB to RDF, the relational mappings. There's a class or a week that we can do on mapping to structured data sources if we have the time. So, but you can remove 2 labs. More questions? No? Okay, in that case, see you on Wednesday. I'm gonna try to change the room if I can. I think we're here. I think we're here like the 3 days, no, Monday, Wednesday, Friday is scheduled here. Are there sockets here? I don't think it's here. Yeah. Yeah. I was gonna make a joke about being in Electrica, one would expect. More sockets. But yeah, so we'll see. We could maybe make it work for this week, but I'll try to get a better room if I can for the lab. So maybe one of the bays at 6 at 8 or something like that. Okay, so see you.